In the previous video, we wrote up the convolution formula, which we were allowed to use since x1 and x2 are assumed to be independent. And what we want to do now is to find the distribution of y equal x1 plus x2. So we want to find the distribution of the sum of x1 plus x2. So let's get started. So what we mean by finding the distribution here is we want to find the density of y and then see if we can recognize the density of y. So let y be given as the sum of x1 and x2. We will calculate the density of y and try to recognize which distribution it belongs to. Okay, so convolution formula, go. We will just use the first line here of the convolution formula. You might note that in the book they use x here and then they integrate with respect to y. The reason why I use y here is because our y is the sum of x1 and x2. So it's just a matter of which names we give the variables. So the density of y, so let's just say let y be greater than 0. And why do I let y be greater than 0 or greater than equal to 0? The reason why I let y be greater than equal to 0 is because that's the only thing that it makes sense for y to be. If y were smaller than 0, then the density is just 0, right? Because certainly y is the sum of x1 and x2, and both of these stochastic variables are non-negative. So let y be greater than equal to 0. Then the density of y is given as the integral from minus infinity to infinity of the density of x1, which they call x1, but I just write f1 because I'm a bit lazy. So it is, let's see, it is the density of x1, which I denote with a 1 down here, evaluated in y minus x, multiplied by the density of x2, evaluated in x dx. So here I just use the convolution formula. Then the next step will be to plug in the values of the densities. So the gamma density for x1 evaluated in y minus x is this huge expression here, where instead of x1, each time I will write y minus x. So this is equal to beta to the alpha 1 divided by gamma of alpha 1 multiplied by y minus x to the alpha 1 minus 1 multiplied by e to the minus beta y minus x multiplied by the indicator function from 0 to infinity of y minus x. And then I'm done with f1, so now I have to go on to f2, which is beta to the alpha 2 divided by gamma of alpha 2 multiplied by x to the alpha 2 minus 1 e to the minus beta x. Am I done? No, I also have to remember the indicator where I need x to be greater than equal to 0. And then I can write dx. So all of this stuff is inside the integral. Sorry, so what do I notice now? What I notice now is I can take the constants out of the integral, right? So I can start by doing that. So I have beta to the alpha 1 plus alpha 2. And then I have gamma of alpha 1 multiplied by gamma of alpha 2. And then inside the integral, well, I can kind of note that I should take into consideration these indicators, right? So what can I take into consideration with these indicators? Well, what I can think of here, first and foremost, is that x should be greater than 0. So I can see that x should be greater than 0 based on this indicator here. So x belongs to 0 to infinity. So at least this lower bound should be 0. But another thing that I can see using this indicator is that y minus x should belong to 0 to infinity. So what does that mean? That means that y minus x should be greater than or equal to 0, which implies that y should be greater than or equal to x. And now, note that we're integrating with respect to x, so this essentially tells us that we can integrate with respect to x all the way up until not infinity, but until y. And y is a number that is given that is also assumed to be greater than or equal to 0, so we're safe here. The integral is still turned the right way around. Okay, so that was the boundary. So we've taken care of the two indicator functions. Now we just go back to the expressions. We have y minus x to the alpha 1 minus 1. And then we have e to the minus beta y multiplied by e to the plus beta x multiplied by e to the minus beta x. So the beta x's and the exponents cancel each other out, which means that I will have an e to the minus beta y, which I can take outside of the integral. So here's where the line goes. Like this is my new line. And then the only thing I have left is x to the alpha 2 minus 1. So this is the expression that I have got to play with. So more or less, the things that are outside of the integral are not that interesting. I just noticed that I have beta to the alpha 1 plus alpha 2. I have gamma of alpha 1, gamma of alpha 2. I have e to the minus beta y. So this stuff here isn't really that interesting, right? The interesting part is what's going on inside the integral. Now, the integral runs from 0 to y, and I really need to figure this out. But this is not easy to figure out. If you try to do this on your own, you will be doing like years and years and years of math, actually. So that is why Stein very nicely gives us a hint, where he tells us if you integrate this thing here, if you integrate this expression from 0 to 1, then what you get is this gamma expression. So this is a result that stems from an area of math called special functions, which you could at one point take as a master's course at this school. I can't remember if you still can do that. But what we know is if we have this integral, then it evaluates to this. However, we do not have this integral because we need a 1 here, and here we have a y. So we need to turn the 1 into a y. And we also need our upper bound to turn into a 1. So how do we do that? Well, first of all, I can notice that if I take y to the alpha 1 minus 1 outside of the parenthesis, then inside the parenthesis, I just have 1 minus x divided by y. So the only thing I have done here is said, well, I can take this outside of the parenthesis. If you want to check this calculation, you can also just multiply this back in again because the exponents are the same, so we're safe here. And then now I have x over y here, so just in a second I will try to substitute that with the v, which means that I will also need to substitute this with a v, which means I also need x over y to the alpha 2 minus 1, and if I want that, then I actually need y to the alpha 2 minus 1 dy. So this and this only, oh sorry, not dy, dx. I integrate with respect to x. So this and this rely only on y, and I can take them again outside of the integral. And when I do that, I can also notice that they actually just kind of go together up inside in the exponent. So I have alpha 1 plus alpha 2 minus 2. And then inside the integral, I can do a substitution. So what I can do is I can substitute x over y with v. Now that will mean that dv dx is equal to 1 over y, right? Which will then mean that dx is equal to y multiplied by dv. So integration by substitution here, guys. And that also means that this upper bound will turn into 1. So now it goes from 0 to 1, and then I have 1 minus v to the alpha 1 minus 1 multiplied by v to the alpha 2 minus 1 multiplied by y dv. No, sorry, not y dv. Well, yes, y dv. Yes, that's true. So now we see that this expression I have down here reminds a lot of the formula that we are given in the exercise that we can use. So the only thing that's in the way is the y, but I can just take the y outside of the integral, and then the integral will evaluate to what we want it to be. So all in all, now we can end this gruesome calculation, a tedious something exercise, by concluding that we get this expression here. So y to the alpha 1 plus alpha 2, and then I have a minus 2 here, but I multiply 1y on top of that, so that's just a minus 1. And the integral evaluates to gamma of alpha 1 multiplied by gamma of alpha 2 divided by gamma of alpha 1 plus alpha 2. And what we see now is that this thing here goes out, and this thing here goes out, and what we're left with is actually a density that looks very much like something that we can recognize. So it's beta to something divided by gamma of the same something multiplied by e to the minus beta y multiplied by y to the something minus 1. And this is the gamma density in the case where the first parameter is alpha 1 plus alpha 2, and the second parameter is beta. So hence, we recognize that y is gamma distributed with parameters alpha 1 plus alpha 2 and beta. So when you take two gamma distributed variables that have different first parameter, if they're independent and you add them up, then what you get is just another gamma distributed random variable with a different first parameter. That is just the sum of the first parameter of the two original distributions.